Good afternoon. So in the up to last class, we looked at MLPs and some basic engineering applications, and then in this recorded lecture, which I'm going to send you, you can look at these 4 applications of MLP in like one is in bioinformatics, that's basic biology, then in 3 more applications in healthcare or medicine. So then after that, I want to discuss this deep neural networks. So MLP is actually, deep neural networks is actually a superfluous kind of technology. We don't need that technology. But what happened was with MLP, generally people assume that it's a single hidden layer MLP, right? And so in the early days, people used to use a single hidden layer MLP more often. And that's also justified because your approximation theorem, assures that you can fit any practical real world function using a single hidden layer MLP. Right, so that's the assumption, underlying assumption. But later on in the last decade, like in 2005, 2006, Hinton and others have shown that if you use a network with a lot of hidden layers, then you can solve very hard problems, and that kind of became a breakthrough of sorts. So although the theory itself was worked out for many hidden layers long ago, because the original theory is applicable even for many hidden layers. So this new incarnation of MLPs, they just called deep neural networks to contrast with the older MLPs, which are shallow in the sense non-deep, which have only one hidden layer. All right, and then that triggered this whole so-called evolution of deep neural network, which is just actually a reinvention. Okay, and people are not able to simulate large networks because of computational limitations. But all that was gone with the availability of better computation resources in the recent decades. So one of the first deep neural networks was happened long before the 2005 or 2006 paper by Hinton. And then this is what we discussed in one of the previous classes. The convolutional network by Lacoon, right, from 1998, 1997 at that time. So this was designed to recognize handwritten digits, and this is architecture of this. Like I was saying, it did very well on very difficult classes of handwritten digits. These are some of the examples we have seen in the last class. Then Hinton in 2006, that was 98. In 2006, they developed this, what is called a deep belief network, where the signal flow or information flow happens in 2 directions. So input data is given to the input layer, and that goes through a series of layers. And the last layer is a classification layer, just like in a CNN. So the neurons respond to that and classify the input. But what is interesting is you can have signal flow going in the opposite direction also. So for example, if you activate one of the neurons in the last layer, the classification layer, that information now percolates downwards and reconstructs an input pattern which corresponds to that class. So suppose you have trained this network on digits, right? Now first neuron in the output layer represents the digit 0. So now if you activate the first neuron, then in the input plane or the input image, you will have a picture of 0 appearing because of the feedback from the top layer. And not only that, the neurons are stochastic neurons, unlike the neurons of the classical MLP. So the input image will be slightly varying with time, right, because of all the variation going on in the hidden neurons. And you will see different kinds of zeros appearing in the input array. So when you activate just the output neuron, one output neuron, you'll keep on seeing different small variations of in the digit 0, the image 0 in the input array. And this is called a deep belief network. And these kinds of networks then start becoming popular after that. Then this group, 5-5 Lee's group at Stanford, they've put out a large-scale visual recognition challenge in 2010, right? And so they put out a lot of images to be classified. And AlexNet, some of you might have heard of this, right? It has taken a data set like that and showed that you can get very high performance. Whereas the best error performance in the first 2 years after the competition was announced was about 25%, and AlexNet, this network by these guys, Brzezinski, Stutzkever, and Hinton, right? This was able to achieve 16% error. So it was a major breakthrough. It's a huge deep network. I'll discuss the architecture of CNN later. When I have a separate class on CNN, I'll discuss in that context. Now, so the neural networks, although the simple MLP, although what we have seen so far is a perceptron and then an MLP, which is a feed-forward network with a single hidden layer, right? And we also have seen RBF networks. Again, it's a single hidden layer, but the neuron model is different. We have a Gaussian instead of instead of a sigmoid neuron. Then we can, if you add more hidden layers to a simple MLP, three-layer MLP, then that becomes a deep network. In addition to that, there are a huge variety of architectures which have been defined and proposed in literatures. So here is a simple kind of these two sheets, these two slides give a kind of a flavor of what kind of architectures, what kind of wide variety of architectures have been proposed in literature to solve various problems. Okay, so we have seen only 2-3 simple examples. Right, and each architecture is good for a certain specific class of applications. So all these developments have ushered in this great AI and deep learning revolution, right? And so the thing is, there's a little bit of historical irony which I need to point out. So both AI and deep networks have begun their journey around the 60s, and in the 60s is when the new network, Frank Rosenblatt has proposed the perceptron. That is, he has taken the Maclaurin bits and then they showed how you can make a learning system out of that. And in the 60s only, the AI has begun, and people started, arguing or thinking that you can reduce any complex process to a series of steps, right? And therefore, you can break down intelligence to a series of steps, and that is your artificial intelligence. And these two methods have begun their journey, and it seemed that although there was a lull in neural networks development during the 70s, in 80s suddenly the explosion of activity and this connections revolution has taken place in the 80s. So after that, neural networks seem to have kind of taken over and then overtaken the AI trajectory. So in the 2000s decade, the first decade of the millennium, then deep networks are reinvented or rediscovered, and that really took off. Because there was a kind of slowing down of neural network research towards the late 90s and the early 2000s. But after deep networks, again, there was a huge explosion of activity. So at that time, it seemed that neural networks were firmly winning the race. So then the AI community did a brilliant move. They said this whole thing is actually AI, right? This whole neural networks and deep networks, everything is actually a part of AI. AI is so big that all these are like special topics, which is total rubbish, of course, because even fundamental tenets of AI are totally different. But anyway, that kind of a move stuck, and somehow people now think that people say AI and deep learning, which is totally nonsense. It's like you may as well say apples and oranges. So that's the deep learning revolution that we have now. So thing is, we have this universal approximation theorem, which says that even a network with a single hidden layer, but a hidden layer which is sufficiently large, can learn practically any function. Right? If that is the case, then why do we need a deep neural network? Why do we need multiple hidden layers? There are several reasons to that, because that's the whole justification behind all the arguments that support deep learning. Why do we need that? First reason is that DNN sometimes give more elegant and structured solutions than a shallow network which has only a single hidden layer. And for example, let us take the problem of parity. Parity is a generalized version of the simple problem of XOR, right? So we know the XOR problem, the truth table of the XOR problem is given in the top right here in the table. So if it has two inputs and one output, 0, 0, if the inputs are 0, 0, output is 0. Inputs are 1, 1, again output is 0. Inputs are 0, 1 or 1, 0, output is 1. So basically in the XOR problem, you are counting the number of ones in the input and you are saying whether it is an even number or an odd number, right? So because if there are two ones, it is an even number. If there are 0 ones also, it's an even number, right? Because 0 is an even number, right? If it is a 1, only 1, 1, it is an odd number. So the output Y indicates whether the number of ones in the input vector is an even number or an odd number. It's a two-class problem. So you can easily, obviously, extend this to multiple dimensions. So in the input, instead of 2 bits, if you have n bits, you can still ask the same question: is the number of ones among those n bits, is it an even number or an odd number? So that is the parity problem. So it's a generalization of the XOR problem. So there's a very elegant way of solving the parity problem, by using the XOR problem as a basic unit. So suppose I want to solve the 8-bit parity problem. What that means is my input vector is 8 bits. Now I want to find out what is its parity. Is it odd parity or even parity? So for that, I can break down the problem in terms of lots of 2-bit parity problems. How do you do that? Look at this tree structure. I hope you can see the mouse moving. Sorry. Yeah, so X1 and X2 are fed into one module. So each of these modules is a 2-bit parity problem. And you know that you can solve the 2-bit parity problem using an MLP, that we have done it in the previous class, one of the previous classes. X3 and X4 are given to another 2-bit parity. If X5 exists to another 2-bit, X7, X8 are given to another 2-bit. Now the output of this network, which says if it is 1, it is let's say odd parity, it's 0 even parity. Right, that one output bit or output variable, I take, like, pairwise. So output of X1, X2 network I take, and X3, X4 network I take, and combine these two outputs using another 2-bit parity module. Okay. So similarly, outputs of the X5, X6 network and X7, X8 networks I combine and feed them into another 2-bit parity problem or parity module. Right, and then finally take in the next level, take these two outputs of these two networks, feed into another network, which is the final network, right? And then you get finally one output. You can easily show, right, that this one output here you get at the top, right, classifies the entire input vector into two classes in terms of the odd or even parity of the input vector. So in this case, we haven't trained anything, right? We have just taken a small network, which solves the 2-bit parity problem, and then it constructed a large network by simply assembling a large network by using this small network as a module. All right. Now, if you can see that this network has one hidden layer. Okay. Now, if you imagine that this network is sitting inside each of these boxes, so you have two hidden neurons here, and then one other hidden neuron here, and then right. You can actually count the number of hidden neurons in this entire network. So you have, this is the first hidden layer, right? And this becomes the second hidden layer, these 4 points, right? And then these are fed in here. Then here again you have, you have two more hidden neurons here, and that's the third hidden layer. And these two feed into another neuron, which is output neuron. This becomes another hidden layer, and these two are two more. So like that, you can see that this whole network which you have constructed by hand, right, is actually a large MLP with many hidden layers. You can count the number of hidden layers: 1, 2, okay, and then 3, 4, then 5. 5 hidden layers, and this finally there's only one output. That's the output layer. So here is an MLP which happens to be a deep network, which has 5 hidden layers and one input layer which has 8 inputs, and this solves 8-bit parity problem. But how did we arrive at it? By simply assembling smaller networks. So what this example shows you is you can by using networks with many hidden layers, you can have elegant solutions to large problems. Whereas if I have to solve the 8-bit parity problem with only one hidden layer, you can train MLP for doing that. You might get a very good result if you take a big enough network. But it doesn't give you any insight into how the network is solving the problem. So this is one example. Another example, another motivation for looking at deep networks as opposed to a shallow network is that DNNs can often learn interesting feature hierarchies. It's a very important term. What that means is lower layers learn simple features, higher layer learns complex features. So let us look at that. Suppose you train a CNN using, on some face recognition problem. So input is a face, which is in a color image with RGB and all, and output is some face classes. Okay, so class 1, class 2, etc. etc. So what happens is in the lowest layers, you will find that neurons simply respond to some linear features like edges and lines and things like that. Next level, you will find neurons. This is actually, you can do this study. So the thing is, once you train a network, you can analyze the network responses and find out what the neurons are tuned to, what kind of features produce optimal responses in the neuron. So you find that you see that this neuron responds to eyes, right? This neuron responds to noses, okay, and so on and so forth, right? So in fact, if you even probe real brains, you will find neurons respond to faces, neurons respond to some inanimate objects, all sorts of things. So basically, all this is you can imagine that it happens for for similar reasons. So in the last hidden layer, some of the final hidden layers of the network, you will find neurons responding to whole faces, but these are entire face classes, whole types of different faces. So for example, this neuron seems to respond to like male face with a mustache. This also, and this seems to respond to a more like a male face but without a mustache. This one seems to respond to more like a female face, and so on and so forth. Because even male and female faces, I mean, it's not a categorical thing. It's a continuum, right? So you can see that some faces look slightly more feminine and some look slightly more masculine and so on and so forth. Now, if you look at the real visual system in the brain, right, that also has a very similar architecture or a breakdown of the image, which is very interesting. Because in the real visual, so this is a picture of a mammalian brain on the right side. Right here, the input coming from the retina, which is from the eyes, first comes to this part, which is called the V1, which is like a sort of like the first hidden layer, or maybe the second hidden layer. And here you have neurons which respond to simply lines, just like in the CNN, which is trained on face images. You will find neurons responding to simply lines or edges. Here also you will find neurons responding to lines or edges, right? And when you go to V2, which is slightly like maybe second or third hidden layer here, you will find neurons responding to not to edges but angles, right? Or even corners. This is a corner. This is an angle. So you will find neurons responding to such features. Then if you go to even higher layers are here, right? And here you will find neurons responding to complex objects, right? Like faces and animate animals and vehicles and etc. etc. Like So this kind of a hierarchy, right? You see when you train a DNN on a complex image, and you see a similar hierarchy even in the real brain. So this is something nice that you get out of a deep network, which obviously you cannot have if you have only one hidden layer in an MLP. Now this kind of hierarchical organization also facilitates knowledge transfer, because if you have a network with lots of hidden layers, right? And so let us say this is faces on this. I'm training this on faces from IITM. Then I want to develop a similar system for face recognition from, let's say, IITB. Obviously, faces are quite similar. So most of the lower hidden layers I can just cut paste and move over to the lower layers of the IITB network, because the actual IDs of the people are different. So only you have to change the connections in the last one or two layers. And if you retrain network, which you can retrain very quickly now, because you have trained only a small part of the network, you will very quickly get a face recognition system for ITB. Okay, so this is called transfer learning, and that is possible because of the hierarchy and this kind of a hierarchical breakdown of the problem in this deep layers. So another thing is this is something called Hastad theorem, which was proposed in the context of Boolean circuits. That is, the Boolean circuits, right? It's constructed out of the three fundamental gates: AND gate, OR gate, and NOT gate. So it says that circuits of depth k, in which only AND gate, OR gate, and NOT gate are used, required size something, right? And so the thing is, if you use networks with Boolean circuit with larger depth, that is more layers, more hidden layers, right? You'll get more elegant, more compact solutions. Now, one more problem is, one more reason why you want to use multiple hidden layers is, there's something called gradient diffusion. That is, if you look at the backdrop algorithm, we haven't gone through it in detail for reasons of time, but so basically, if you look at Wij of the second layer as opposed to say Jk of the first layer, so what happens is one of the terms in this, you have a lot of terms. One of the terms, if you expand it out, is a G prime term. The G prime terms comes hidden inside the delta variable. This G prime term for the first stage weight, so this is the 3-layer MLP. So this is Wij second stage. This is Wjk first stage. So for the first stage weights, when you're in the update equation, G prime shows up in one place. In the second stage, and for the first stage weights, G prime shows up in two places like this. Now, what is G prime? G prime is the derivative of G. G is a logistic function. So G prime looks like this. Now, the highest value is lambda, but lambda is slope of the logistic function. But it will fall very quickly as you move away from the origin. Okay, so therefore, G prime is typically, is likely to be low, right, more than high. Now, if you have multiple terms like this, and if you have product of all those terms, right, that will kill the value on the right side. What that means is, because of this factor, the update, weight update in the lower layers will happen more slowly than weight update in the higher layers. So if you have a deep network, then weight update in lower layers will be much slower than weight update higher layers. For this reason, when you want to have a deep, when you want to have a solution, you may as well use the pre-trained weights from some other network, right, which is solved on a similar problem, and carry it over. Now, this is a facility that you have possible only when you have a deep network. The deep network will have a problem, but the same problem also points to a solution, because you can always carry your pre-trained weights from one network to another, which is trained on a similar problem. Okay, so it's also the problems with training MLPs, large MLPs with backprop. There are multiple approaches. So it is with backprop, you have to backpropagate the deltas from the last layer all the way to the input, and that can be computationally expensive. So what people do, one approach to solving, training very large networks with large number of hidden layers or very large deep networks, is to use unsupervised learning for all the hidden layers, and only the last hidden layer, last stage, right, is trained using supervised learning. Okay, so that way the training can be faster. So this is a kind of a hybrid learning, because you're using two different kinds of learning. What is supervised learning? In supervised learning, there is a teaching signal. What is a teaching signal? This is the desired output. Right? The desired output is defined. Whereas there are learning algorithms where there is no such thing as desired output. So we haven't discussed. Okay, clustering is one such example, right? So although I didn't discuss unsupervised learning in the context of neural networks, but clustering is a great example of unsupervised learning, because we are not giving any class labels as input to perform the clustering process. We just have the distance measure, similarity measure, and that's all there is to it. Only in classification we give class labels. So classification is a supervised learning method. So for example, classification. And the clustering is an unsupervised learning method. So clustering, unsupervised learning is faster because you do it without any teaching signal. So therefore, one approach to speeding up training of large networks like this is to use unsupervised learning for the lower layers and use only supervised, because the target output or desired output is defined only for the last layer. There's nothing like a desired output for hidden layers. Right, so you train only the last stage using supervised learning. Whereas the other approach is what we have been discussing all along, that is backpropagate the error from the output layer all the way to the first hidden layer and then train everything. That is what we do in backprop. So in hybrid learning, like I said, you use unsupervised learning up to the last hidden layer, and from the last hidden layer to the output layer, you do supervised learning. So this unsupervised learning, right, of the network up to the last hidden layer is done like this. So one way to do it is using what is called the autoencoder approach. So let us spend a little time on that. Suppose I have my input layer, which I'll call layer 1, and first hidden layer which is called layer 2. So then what we do is you add a next layer which we call layer 3, and layer 3 has as many neurons as there are in the input layer. So note that in the input layer there are only 6 neurons, and this plus 1 is the, so what happens is the bias term that you have for every neuron, every sigmoid neuron, is often implemented as a separate. So let me explain that. Okay, so if I have a neuron which has many inputs, it also has a bias term, right? B. So one way to handle the bias term to make programming more easy and even the mathematical formulation more elegant is to simply, so let me call this x1, x2, xn. So weights are w1, etc., wn, and there is a bias term. One way to deal with the bias term more uniformly is think of it as the n plus 1th input. So this is x1, x2, xn. The weights are w1, w2, wn. Now you think of this weight, this bias as b, which is the weight of the n plus 1th input. And the input to that, if you want to make this plus 1, make this value minus b. Or if you want to make the weight b, then make the input minus 1. Right? So you can replace this n neuron, a neuron with n inputs with a neuron with n plus 1 inputs. Only thing is for the n plus 1 input, you have a weight which is equal to this bias parameter. So that way, the math will become more uniform. So you don't have to deal with the bias term as a separate kind of a variable. It's also one more weight. Okay, so that's what they're doing here. They are adding extra input to the input layer, this plus 1, and then the weight here from going from this plus 1 unit to the hidden neurons, this weight represents biases. Okay, so that's just a small hack and it's not very important. Now, so the input has 6 neurons. Now, in the output layer also there are 6 neurons. So the way you train this network using unsupervised learning is, let's say I have the input vector x here, and output vector is we'll call something h of x or whatever. The desired output for the output layer, I'll call this x. So d is equal to x. So the desired output of the network is equal to the input vector. This sounds like a silly problem. Why do you want to do that? Because why do you want to map a network that takes input x as x and produce x as output, which sounds absurd, but there's a very interesting purpose in doing this, because when you try to do that, the hidden layer will learn a very nice representation of the input. Okay, by training this network in this artificial fashion. So let us look at that in more detail. So the output of this network is some h of x, right? The desired output is defined to be equal to the input vector. So when you do that, see what is happening here. The input has 6 neurons. The hidden layer here has only 3 neurons, and output again has 6 neurons. And let us assume that you're able to get back your 6-dimensional input in the output in terms of the 6-dimensional output, right, quite accurately. But to get the 6-dimensional output, right, you are able to get it only using this 3-dimensional hidden layer, right? If you succeed in doing that for all the input patterns, for all the training patterns, that means you are able to reduce the dimensionality of the input from 6 to 3, right? Because even from the 3-dimensional reduced versions of the input, you're able to reconstruct the output, which is actually the input itself, right? So you are mapping, let me call this okay, Z. Okay, so you are mapping X to Z to, I'll call this X hat, which is the reconstructed. So X is n-dimensional, Z is m-dimensional, X hat is again n-dimensional. So here n is greater than m. Okay, so you're able to reduce the dimensionality of the input and then recover it. So how do you know that the reduced dimensionality is good enough? If you're able to recover the input x here accurately, we can have some kind of a margin there, some threshold there. Then the reduced dimensionality is working well. You're able to express that input vector into a smaller dimension. So this becomes a representation of the input, but in a smaller dimensional space. Okay, so once you do that, right? Once you achieve that kind of a transformation, then I don't need this output layer anymore, because all that the reason I want to use this output is just to define the problem and calculate its representation. Once I calculate the representation, I don't need the second stage weights anymore. So I remove those weights and remove the output layer. So at this stage now I have and I succeeded in adding one extra layer. So I have input layer which is six neurons. To that I added another layer which has only 3 neurons. Okay, like that I'm able to construct one layer, and in this process I haven't used any desired output at all. I haven't used any desired output which you actually use in the final layer, the output layer. Now what you do is you have the input layer, then the first hidden layer, then you add one more hidden layer, and then another output layer. Okay, so now the input that you originally have, right, that is presented to this layer, and there's now this layer output becomes the input to this network. So for this whole network, right, which you are now considering, this A1, A2, A3 becomes the input, and B1, B2, B3 is the hidden layer, and whatever it is in the output which shows blank circles is the output layer. Again, you do the same thing. The target output of this network is A1, A2, A3. This is the target output. So basically, it's trying to map the input onto itself. And again, you assume that you're able to come up with a good mapping. The error is low. That which means the B1, B2, B3 are able to encode the information present in A1, A2, A3. Right. So now the purpose of this output layer is gone. Remove it. Remove the weights also. Right. So now you have original input layer with 6 neurons and 2 hidden layers. Okay. Now you do the same thing over and over again. Right. You add one more layer and add one output layer and then train from here to here. Right. Every time this is like a bootstrapping. Every time you add one extra layer. Oh shit. Okay. So you add like that, and finally when you come to the final layer, this is where you actually present your original desired outputs. Okay, so from here to desired output, this you train using any supervised learning method, and that can be like in your perceptron learning rule, like what is called the LMS, least mean square learning rule. So that is a hybrid way to train a large deep network. Now, what we'll do is next class we'll look at the convolutional network as a special case of a deep neural network because it has a specialized architecture. Then we'll describe the various applications of deep networks and convolutional networks in biology. So this we'll cover over the next few